Hari Raya. Okay, so I was thinking on choosing the date 11/5, 11 May. 11 May is in the second week of Hari Raya. Okay, Wednesday, and we choose the evening time. Okay, it's only and 1 hour for the test. So how about if we begin your test one on Wednesday, 11 May 2022 at 2:30 p.m. Is it okay?
Hi, doctor. Can you repeat your last statement?
Okay, so I check put in the chat box Wednesday 11 May. Can you see that in your chat box? So your
Yes,
class
doctor.
one will be on the Monday. Sorry, Wednesday, 11 May, 2:30 p.m. Okay? Yes, yes, Siva Sangari. Any question? You raise your hand. Okay, so we stick at the moment we stick the date on the 11. Okay, usually we don't have any class on a Wednesday, so that's only suitable time to replace for the cuti hari raya. Okay, hope everyone okay. Okay, then I will put it. I will acknowledge back the test one date in your e-learning soon. Okay. All right. So today I'm going to continue our lessons. Okay, about the compressible flow. Okay, I hope I can finish everything by this week. Okay, on Wednesday, I hope I can finish the second chapter, compressible flow, and later you can concentrate your time. You can spend your time for doing your assignment 2 and preparation for the assignment number 1. Okay, so today I'm going to explain about this is the new things in compressible flow. Okay, the last part of the subtitles, the subtopics. So I'm going to teach about the shock waves and the expansion wave. So for some back pressure values, the abrupt change is a sudden change in fluid properties occur in a very thin sections of converging to diverging nozzles under supersonic flow conditions, creating a shock wave. Okay, so the phenomena occurs in the converging to diverging nodes, and this phenomena, okay, the other terms we call it as a shock wave. So we study the conditions under which shock wave develop and how they affect the flow. So there are few types of shock wave, and uh, the first one is the normal shocks. Okay, the normal shock. Okay, so let's see the diagram. Okay, that visualize in your right screen. Definitions of normal shock wave. The shock waves that occur in a plane normal to the directions of flow. So the keyword is normal. Okay, the flow process through the shock wave is highly irreversible. Okay, so it means that this is the shock wave. This is a normal uh, shocks. Okay, so the flow, the normal shock is perpendicular with the pole directions. Okay, it means that now imagine the flow of the fluid in a supersonic. Then suddenly there is a change of the velocity speed, the fluid velocity, okay, from supersonic to the subsonic. Dia tengah bergerak, tiba-tiba dia break. Okay, then this phenomena will create the normal shock. Dia macam kata gelombang kejut. Okay, so this is the normal shock. And you can see in your right screen, this is the normal shock image, okay, in a level nozzle. The Mach number in the nozzle just upstream is the right, uh, to the left of the shock wave is about 1.3. The boundary layers distort the shape of the normal shock near the walls and lead the flow separations beneath the shock. Okay, so this is the phenomena of normal shock. Okay, in a control volume for flow across a normal shock wave, okay, this is the control volume, the conduits, okay, then the Mach number more than 1 is a supersonic flow. Then there is a sudden change of velocity speed, the air velocity, then it will create this red line. The red line we call as a shock wave. Then the properties before the shock wave is denoted by subscript number 1, while the other properties of the shock wave denoted as 2. All right. So this is the phenomena, the basic understanding about the normal shake. Supersonic to the sonic and in the normal directions to the fluid flow. So there are some important equations related to this topic. The first is conservation of mass. Okay, so given by rho 1 A V1 is equal to rho 2 A V2. Okay, it means that the before is same to the after. The downstream, the upstream equal to the downstream. So because of the same uh, area, so we can say that the rho 1 V1 is equal to rho 2 V2. Then for the conservations of energy, this is the thing that what we've been learning 2 weeks ago. Okay, the H1 plus V1 square over 2 will be equal to the H2 plus V2 square over 2. Okay, so the upstream equal to the downstream. The before same to the after. And the conservations of momentum denoted by this formula, you take the area and then P1 minus P2 is equal to mass flow rate M2 V2 minus V1. Okay, and then this is another important things. When normal shape occurs, there is an increase of entropy. Okay, the entropy given by S2 minus S1. Then this entropy must more or equal than 0. Then next we see the phenomena. This is the enthalpy versus the entropy for the shock wave. Okay. In a phenomena, combining the conservations of mass and energy relations into a single equations and plotting it on a HS diagram yield a curve. So this is phenomena. So it will create a curve. Is it is the locus of the states that have the same value of stagnation, enthalpy, and mass flux. Okay, so this is the phenomena, and this is the shock wave that occurred to before the uh, in the system. Okay, so the rail line is combining the conservation of mass and momentum equation. Okay, and plotting it on the HS diagram. So the phenomena is a combining of conservation of mass and energy. Okay, while for the relic line is a conservation of mass and momentum. Okay, so the conservation of mass uh, is including in the calculation for both Fano and Rayleigh lines. However, there is a change in the energy and the momentum. So this is the Fano line, this is the Rayleigh line, okay, and this is the shock wave. Then the relations between various properties before and after the shock for an ideal gas with constant specific heats. Okay, difficult to spell out one by one. So I can say the ratio of temperature, okay, before and after T2 minus T1, when you put into the account, okay, final equation will be the ratio of pressure, okay, square multiply with the Mach number ratio. Okay, so before, after and before. This is for the T2 minus T1. Okay, while for the pressure, the P2 over P1 will equal to a Mach number at 1. Okay, so square root 1 plus Mach number 1 square K minus 1 over 2 divide with Mach number 2 square root of 1 plus Mach number 2 K minus 1. Okay, divide with 2. And the Mach number at the downstream is given by the formula MA2 is equal to MA1 square plus 2 divided with K minus 1 divided with 2 minus 1 square divided with K minus 1 minus 1. So don't force yourself to memorize, but practice yourself of using this formula. Okay. Uh, so for your test and final exam soon. Okay, for the this is the variations of flow properties across a normal shocks for an ideal glass. So there is an normal shocks in the system. So the the properties will also change. Okay, some of the properties increase while some of the other increases, and some of it remains constant. Okay, so the phenomena of normal shock can be seen in the air inlet of a supersonic fighter. Okay, so the air inlet of a supersonic fighter jet is designed such that a shock wave at the inlet decelerates the air to subsonic velocities. Okay, so this is very important to control the air speed. Okay, for not damaging the engine, the aircraft engine. And then as you can see, uh, the image, this is actually the view, the top view image for the blast wave, okay, produced by explosions of a firecracker detonated inside a metal can that set or stool. Pernah tengok kan kalau ada satu letupan, lepas tu ada macam lengkungan, macam nak kata asap ke asap, tapi asap yang mewakili wave tu dalam bentuk macam bulat kan. So that is the normal shock wave. Okay, and then the change of entropy, as I mentioned just now, this is the important parts of the uh, this section about the entropy change. Okay, so always in your mind that entropy change must be the change of entropy. Okay, so the S2 minus S1 before, after, deduct with before, and given with the Cp ln T2 over T1 minus R ln P2 over P1. So this is the entropy change across the normal shocks. Okay, since the flow across the shock is adiabatic and irreversible, so boleh balik ya. The second law of thermodynamics requires that the entropy increase across the shock wave. It means that there is a change of entropy. Okay, even though the change is small, but there is a change in the entropy. Okay, across the shock wave. Thus, a shock wave cannot exist for values of Mach number 1 less than the unity, where the entropy change would be negative. Okay, so it means that uh, uh, it must always has the change of entropy. For adiabatic flows, shock waves can exist only for supersonic flows when the Mach number is more than 1. Okay, so like I'm saying that it must be in the supersonic conditions. Okay, and that's the reason of right of this statement. Okay, so the point of maximum entropy, the phenolene, I don't want to go in detail about the way of solving. So you just see from h plus v squared versus constant and differentiate this equation, you get the h plus v over d 0. And for a very thin shock with negligible change, the area across the shock, the steady flow continuity conservation of mass given by rho v and equal to constant. Okay, so you get that when you differentiate, you solve, divide with the dv, you get this formula, and then we combine with the energy equation. Okay, v square dp over rho, and then go down. This is the v. So v in the equation form. Okay, next I'm going to explain about the example, the shock wave in converging to uh, diverging nozzle. So this is example 12a, the shock wave in a converging diverging nozzle. Okay, so let's read the questions together. If the air flowing through the converging to diverging nozzle of example 12.6 experiences a normal shock wave at the nozzle exit plane. Okay, as seen in this figure, so there is a normal shocks at the exit plane. Determine the following after the shock, the things that we want to calculate, okay, after the shock. First is the stagnation pressure, static pressure,